Neo4j meetup group, and I saw you were going to have this introduction like 2 years ago, just before the, or just when the pandemic hit, and you had to cancel it.
Yeah.
So that's a shame. So then
Let's do it.
coming that way. So that now you.
You're righting a wrong in history. That's fantastic. So for those of you in the room who maybe didn't hear that, this was, our hosts from actually Malmö Data Science, right? It's the Malmö Data Science group. So shout out to Malmö Data Science. Thank you for bringing me here today. We got the backstory and how we got invited here. I'm Andreas Kollegger from Neo4j. I'm presenting to the Malmö Data Science group. And today we're going to learn about data science using a graph database. Neo4j is a graph database. Don't worry if you don't know what that is. We're going to explain that and then explain some data science you can do with Neo4j. And if anything, actually, the backstory and how I got here is itself a small encapsulation of a graph problem that was solved by finding within your network, who do I know that knows about Neo4j? Let's bring them here to this meetup and make it happen. So well done that. Good setup for it. For all of you, I know this is the data science meetup. I am not a data scientist, so that's important to keep in mind as we go through this. But the beautiful thing about Neo4j and this particular sort of library that we have around Neo4j and graph data science is that I can do data science, even though I don't necessarily know what I'm doing. I can get the value out of it because I understand how to use some of those algorithms to get useful things out of it. Could I write those algorithms? Probably not, surely not actually. But I can use them and actually apply them to graphs and actually get useful stuff out of it. So that's what I'm going to talk about. The reason I can do that is because in addition to Neo4j, which is a graph database, so it's good at having a graph structure, storing it, getting that back, querying it. We also have this fantastic library called GDS, which is a graph data science library that has all kinds of fantastic algorithms that do lots of magical things that, well, to me are magical because they're just beyond my ability to understand how to implement on my own. So we'll start with the basics. What actually is a graph? And I should point this out, I'm sure you guys don't need this, but for everyone out in the audience, I'm not talking about charts. Neo4j is not a database for creating a pie chart and then storing it and then retrieving it. That is not it. We're talking about graphs. We're talking about the classic circles and lines of a network or a graph, which is, of course, backed by graph theory. Neo4j as a database says, hey, that's an interesting structure. For each of the circles and each of the lines, let's just use that as data and then see what we can do with it. Graphs, of course, have become more popular thanks to things like, Facebook, which has popularized the idea of a social network. People are like, oh yeah, a social network. It's not just people who know other people. That forms this data structure that is a network. Can we do stuff with that? Neo4j is the kind of database that lets you do stuff with that. If you have a telecom network, any of the things that are networks, you can use a database that is Neo4j for storing that network. In graph theory, there is, of course, the classic use of graphs, which is I've got a place in the world. How do I get to this other place in the world? Graph theory helps with those kinds of problems of how do you find your way around the world through routes, whether there's physical routes in the real world or it's a network or anything else. And maybe not as obvious, but very popular for graph databases, and this starts to get into some of the actual graph data science, is that a graph database turns out to be fantastic for doing things like recommendations. Like if I know you and you know him, and you've bought a shovel and I'm out shopping, maybe I should also buy a shovel. That's a terrible example, possibly. But it turns out that some of the patterns that emerge for actually how do you do recommendations, whether it's somebody that you should follow or some product that you should buy, are just simple graph patterns. So once you understand how a graph is and how to query a graph by describing patterns, you can actually apply that for things like recommendations. One of the more well-known algorithms that we'll touch base on is from our good friends at Google, who became a reasonably successful search engine because they had this algorithm called PageRank, which is really just a graph algorithm for how do you actually figure out what pages in the internet based on the PageRank algorithm are actually useful when you search for something, rather than just what are the most keywords or any other kind of metrics. The position, topological position of a page actually matters. Then it extends also into, these days there's a very popular trend around knowledge graphs. Obviously graph is in the word there, or in the name there, so Neo4j is perfect for that as well. If we start to get mathy about it, of course, a graph and graph theory or just a network structure, we know can be undirected, it can be directed, or it can be weighted. These are the basics of actually having a graph traditionally drawn as circles and lines. Those lines representing edges, we would say, and each of the circles, we would call them nodes. In Neo4j parlance, we actually say nodes in relationships. You could have them undirected, you could have them directed, which means this blue dot goes to that green dot. And any of the edges themselves, typically the edges and not the nodes as much, you can add values to, so that if you're doing something like a pathfinding from here to Stockholm, you can figure out the fastest way to go based on the cost or the speed you can go on all the roads, or the cheapest way to go based on the dollars cost or the sec cost for actually traveling from here to Stockholm. That's just a basic graph query. If you want to do computation on a data structure like that, you turn to something like an adjacency matrix, where an adjacency matrix for this particular small graph here is just nodes on one side, nodes on the other side, and wherever there is a relationship from this side to that other side, you put a number. You say, okay, B goes to A. Where's my B? Here's B. B goes to A. We're going to put a 1 there saying, true, there is an edge from B to A, a directed relationship at that point. So once you've got something in a matrix, you know probably better than I know that you can do all kinds of math stuff with it. Math is good, math is powerful. For Neo4j, as a database, we actually don't start by thinking about adjacency matrices, though. We'll come back to the adjacency matrix and actually doing computations and algorithms with Neo4j in a graph. But we start by thinking about it as an information architecture, where the information architecture is something we call a property graph. And the property graph means that for both the circles and the arrows that go between the circles, those are just data records to us. If you're familiar with relational databases, you can think about these as being tables and join tables between other tables. It gets a bit more interesting because each of the tables are not exclusive. So here this is a person. We call that, instead of a table, there's a label called person that this node has as an attribute. But then the label ends up being a way of grouping all the things that might be a person. But it's not exclusive. You could also have person, and you could say that you want to have a subset of persons that is customers. You don't have to create a separate table for that. You just say, okay, well, this person is also a customer. And you add a new label. It's as if nodes as a data record can belong to multiple tables. Relationships are a little bit different than that. Relationships only have a single type. They can't have multiple types. So if you want to have, this person loves that person, they'll love them back. If they also live with that person, that's a new relationship. You can't have multiple types on a single relationship because, of course, relationships are exclusive in a property graph model sense. Right, and then the actual data that you add there is basically a small, arbitrary key value pairs that you can add. So if you want to have values like this person's been driving this Volvo since this particular date, you can add that to the relationship. Of course, you can say things about the Volvo itself, like what brand it is and what model it is. And this is a descriptive schema rather than a prescriptive schema. It is schema-free or schema-optional, I guess you would say, where when you start to create data, whether you're just drawing it on a whiteboard, you're not first constrained by what you're drawing on the whiteboard. You just draw what you understand. For the most part, that's how you work with Neo4j. You just actually capture the data that you have in a graph shape with things that are connected to other things. And over time, the data itself is the schema. The data that you've put in there represents something rather than starting with the point of saying, okay, here's what I'm going to allow, and making the data fit into that. And we'll come back to that idea a little bit later because you'll see why that ends up being super powerful for Neo4j and for graphs generally. The other points here, the low cognitive load and that you can do all kinds of insightful things with it. That really touches on the aspect that I think there's a lot of natural intuition we have around graph data structures. Even simple things like, if you want to find a job in some place down the road, or if you want to find somebody to talk at a meetup, you actually in your head start to think in very graphy ways. You're like, okay, who do I know that knows this topic or that works at that place? And do I know somebody who knows that somebody? And then you kind of work through your personal network to find connections. That intuition, maybe surprisingly, applies across all data sets. That within all data sets hidden, there are relationships that are either explicit or that you could derive out of the data set. And that intuition you have about how to do things applies equally to any domain within graphs, which is crazy. But one of the reasons why GDS is so powerful. Okay, so we've covered, actually, I think all of this stuff is already. Neo4j is a graph database. It's got a property graph model as the data structure itself, and it's a database. So you can put, get, and query for stuff. One of the other intuitions, which I think maybe I touched on, but like, if you're very familiar with relational databases, you understand tables, you also understand join tables. One way to think about relationships is that they are as if you have this giant join table where all of the joins have been pre-calculated, which ends up meaning a little bit that you've kind of paid at write time for an optimization. It's a little bit like the benefit you get out of using indexes or something else, that as a database and as a data structure, graphs kind of optimize for doing queries across tables, is one way to think about it. That plays out all the way to the query language itself. We have a query language that we call Cypher. Cypher takes a lot of inspiration from SQL, so it has clauses like SQL does, but it is focused much more on describing patterns and then having predicates that apply to that pattern. And then you do the usual kinds of things where you can have, aggregates that you report back or those kinds of things as well. If you would try to read these two queries, the top one here being in Cypher, our graph query language, and this being the equivalent in SQL, maybe you know SQL well enough that you can understand what this one is doing. This top one is fun because what we're doing is, if you just kind of read it out, we're matching a pattern that is some product that's in a category where the parents of that category, up between 0 and 3 steps out, are in some product category that the name of that product category is 5G products. You can say that a couple times to yourself and start to think about, okay, what does that actually mean? You'd probably realize what that means. You're just traveling up from a category up to the parent categories, arbitrarily depth between 0 and 3 up to that root pattern. So you know that you're looking for all products that are essentially in this subset somewhere of this 5G products supercategory. To say the equivalent in SQL, you of course do a bunch of joins. Now the logic is exactly the same, but the meaning is more obvious in Cypher. So Cypher is optimized for doing graph query patterns across records. You can do that same effect in SQL, but it's much harder to express, and the intent is lost. Somebody else who doesn't quite know what you're doing here has to really squint at it to figure out what you're doing. If those are the kinds of queries you're writing in SQL, then probably you already have a graph problem, probably actually want to use a graph database for whatever you're trying to express. As a bit of an anecdote, when Neo4j first came into the world as a thing, this sort of expressivity problem was part of the motivation. That in the domain that the founders were actually already working in, the problem that they had on hand, they already had relational databases. They already had tools at hand to do the work, but just writing the queries was taking so much time that they essentially invented like, hey, can't we just have a framework that lets us writes those queries for us, but expresses the queries in terms of essentially this kind of pattern matching. From that, rolling forward all the way to today, just kind of the natural evolution of like a problem that was interesting that lots of other people had got us all the way to like Neo4j being a database, in its own right. Okay, so back to the data sciencey part here for a little bit. So great, this is a graph database. It has this data structure. How do we use this for doing data sciencey type things? And when do you use it? Of course. This is pretty obvious. It's a bit of a tautology, of course. Use a graph database when you've got a graph problem. Right? That's the time to use it. No disagreement there? Everyone's thumbs up. This is the thing to do. Okay, great. I worked a lot on this slide. I was hoping I'd get more reaction on it. But, so how do you actually know that you have a graphy problem? In my, drinking the Kool-Aid heart of hearts that love graphs and see graphs everywhere, of course, I see everything as a graphy problem. But more specifically, I know that for anything that I look at, I can derive a graph from that. Either there already is connections in the data set, either you already have foreign key relationships and those kinds of things, or there are implied relationships that you simply can derive. There isn't a data set that is interesting that doesn't also have relationships. Now, whether or not you care about those relationships is a different matter. And the reason you care about those relationships is because it gets you better results. That's really the motivation for this stuff. I told you a little anecdote about how Neo4j started. Neo4j started by actually just trying to write these queries that were graph-based. What we wasn't realized at the time, and now we're much more appreciative of, is that once you've got that structure and the ability to query across that structure, the data itself, the individual nodes that you've connected, become richer because now they're not just information about this particular node, it's also about all the nodes it's connected to and the nodes that those things are connected to. You just automatically created more value out of the data that already exists just by connecting it to other data. It's another dimension of the data that you can choose to ignore. If it doesn't matter to you, then it's fine, but you can take advantage of it for particular cases. So, as an example of that, for an area called churn prediction, which whether it is a political churn in like, who's going to be the next president or other elected official in various parts of the world, or if it is customer churn or any place we're concerned about, for the people I know about that are members of something, what's the likelihood that they will continue to be members? Perhaps even for Foo Café, perhaps even for viewers, what's the likelihood that one of you is going to change the channel? Very, very low, right? Because, right? Also, if I want to understand that better, one of the best predictors for whether or not you're going to change the channel or you're going to change their customers or change the elected officials has less to do with the kind of the information contained in that individual than it is about the relationships that that individual has. That kind of, again, intuitively, the more relationships that a person has, the more stable the network around them, the less likely you're going to drop all those relationships to go do something else. So if you have a lot of friends here in the room in Foo Café, you're more likely to show up to the next Foo Café event, both for the content of that particular event, but also because your friends are going there and just the nature of being humans, we happen to behave in that way, right? That applies across lots of different domains. So churn prediction actually is more accurate when you take into account not just the individual properties of a person, but what are the connections that person has. The more connections they have, either to other people or to other things, the more likely they are kind of embedded in their environment. We're going to extend this to a couple of will it graph situations to see, is this potentially a graph situation? For facial recognition, which starts off, of course, with just taking an image of a face, digitizing it, and then looking at a bunch of pixels, you can stare at all the pixels, and that's good. That's certainly a place to start. You can train models on just the pixels. Super good. That's a good place to start. But way more efficient is if you actually know something about the face. If you actually know something about the domain, it's not just that there are random pixels here that happen to be eyeglasses and a microphone and a wave of hair and all these things. If you know that this is a face, you expect there to be a density of pixels here for my eyes and a bit of a smile. You can actually look for patterns in the data that are beyond just the pixels individually by themselves. So in a series of illustrations here, image recognition, facial recognition, whether it's actually for faces or for anything that you know the overall kind of structure of what you're expecting, it's easier and faster and more accurate to actually take advantage of that structure. And you do that by actually saying, okay, there's going to be a mouth, there's going to be a nose, there's going to be eyebrows. Look for those things and then optimize around those regions and how they're connected. And if they're not connected, if there's an absence of that feature, if I've shaved my eyebrow, am I possibly hidden from the facial recognition? Definitely at some point, if you lose features, you no longer have a face. Areas like drug discovery, this might be, I think, intuitively more obvious. We know a lot about how drugs are very complex, in and of themselves, but they have very common building blocks, and those building blocks and like that end up, creating proteins and other medical things that I'm not even going to try to remember the names of. But if you're doing drug discovery, you can take a look at the body of data and realize both in terms of the structure of the drugs themselves, but also into the things that they apply to. You can put all that into what essentially is a giant graph. And the recommendation I was talking about before, you could basically look for recommendations of like, hey, this drug worked for this, and it worked for that and that and that. And actually, all those things are similar to this other disease. So maybe this drug works for that other disease. That kind of thinking, once you start to apply it, once you start to realize it and then apply it to any kind of domain, it just extends anywhere. It's the same patterns, it's the same approach. Natural language processing is another easy one to see as a graph, because we know, of course, that language is highly structured, even as fluid as it is, even as many fill words as my language has. You can filter those out. You can get to the meat of what I'm saying, and actually then break that into a graph and actually do analysis of the graph and probably predict what I'm going to say next, or based on what I've just said for the last 15 minutes, however long it's been, probably generate the rest of this talk and maybe be as funny as I am. I'm not sure about that, but with a bit of work, that's possible. Body composition analysis, this is another one. And actually, if I can I have just a quick time check? I want to make sure that I'm tracking okay. Where are we? Oh, fantastic. Okay. A lot of time. Well, good. We're going to try to get a demo in as well, so I will be a little bit quicker through this next part. Body composition analysis, it's the same idea based on body types. There's lots of information we know about a body, but if we know not just the information, but like how that information is connected to other pieces of information, you can do more analysis. Let's get back to actually creating a graph and then doing useful things with the graph. I previewed this earlier that a property graph model is just some nodes and some edges between those nodes. So that's how you create a graph. You just get a bunch of nodes, figure out what the things are generally, and then what are the relationships with those things? Are they peer relationships? Are they actions? Are they actually behaviors? Are they events that happen? Figure out what the stuff is that you have in your domain that connects the things in your domain, and then put that into a graph model. It is nice that in, again, the graph model, you don't have a schema up front. So if you just want to start with just whiteboarding away and just taking the data you have and just trying out things, there is a kind of schema evolution that happens, a data evolution with graphs where you don't have to be perfect up front. Start with what you know, and over time, you end up kind of iterating on the same data model and really enriching it. The rule of thumb generally with graphs is start as simple as you can and then worry about elaborating over time. Don't try to have the perfect model of like that's going to predict what you need 5, 10 years from now. You can evolve the model over time. And actually, I'll come back to this point in a few slides. So you get a list of nodes, you get a list of edges, you mash those things together and you get a graph. This is the slide that is about the importance of graph evolution. This is maybe hard to see, but this is the Game of Thrones. This is essentially the data model that is the Game of Thrones put into a graph. This visualization is taken from Neo4j's built-in data modeling or data visualization tool called Neo4j Browser. And if you look at the colored dots, there's a handful of those, but there are way more relationships. Now those are interesting in two different ways. The nodes are easier to understand. It's easier to see. I've got a person, I've got a castle, I've got places. Those things are easier for us to catalog. What's less obvious, but you don't have to worry about as much, is all the complex relationships potentially between these things. And in most domains, you start off with very simple relationships, very direct one-to-one relationships like I know you. Fantastic, that's a great place to start. But over time, as you work with data, one of the nice things about not having to worry about schema is that if you realize there are more relationships, like not only do I know you, but I work with you, fantastic, I can add that later. You can continue to elaborate on the data model, and over time, you end up with many more relationships than you do nodes, both in the kinds of relationships you have, the types of relationships, there are more of those than there are types of nodes, and in the overall volume. You'll probably have something like an order of magnitude more relationships between nodes than you have individual nodes themselves, which obviously is a huge, rich source of data that's worth taking advantage of. As far as the number of nodes in this particular graph for the Game of Thrones, again, just using Neo4j's built-in visualization, here's a sample of the data. And all of the eyeballs here, and maybe the eyeballs online as well, will start to look at this, and you'll see the colors, and you'll do what people do. You'll start to do the pattern matching. You'll be like, okay, what are the patterns that are here? And you'll start with the colors. Okay, I see things that are orange, things that are blue, things that are light blue, maybe pink. And yeah, okay, you're already drawing intuitions from this. You'll then see that there's a bunch of lines, and those lines are hard to make out. It's hard to actually derive information out of those lines. And yet that is the wealth, that is like the dark matter of data, where it is omnipresent, it is everywhere. And if you can actually highlight that and use that, that is huge. That is incredibly powerful. So even though we're going to focus on the records, the data, the nodes themselves, when we look at this, it's the relationships that are just beyond our ability to follow because there's so much there that we're actually going to tease out with graph data science and with algorithms. And so let me talk about what that means. So once we've got something that's in graph shape, and for my argument, of course, all the value is in the relationships in the data. How do we actually work with that relationships and derive value out of it? There's an easy one here. This goes back to the nodes, but it's based on the relationships. And it's centrality, like what is the most important node in that entire Game of Thrones? How do you actually figure out what the most important node is? There's a few different algorithms you can use for that. They're basically all kind of in the overall family of centrality. PageRank, again, is the most well-known, but these all do essentially the same kind of iterative process to try to figure out for a given node, for all the nodes, how important is that node within the overall graph? If this node disappeared, does that matter? Does anyone care? If that node is a friend of ours, do we want to be that person's friend? This gets into influencers and all those kinds of aspects. As some examples, for centrality algorithms, it's degrees, wait, oh, there it is. Sorry, there we go, okay. So as two simple examples, if you had a telecom network, again, within a telecom network, it's super useful to know that if a given power supply goes out, here's all the customers that are going to go down. Here's the part of the network that's going to go down. Are you going to lose an entire region because that power supply went down? It's useful to know. It's also useful to know either because disaster happens or because you're planning some maintenance and you're like, oh, some guys are going to go out there with a truck and turn off the power, and what's going to happen? It's good to know before you turn off the power. As a different example, if you have a graph that is a supply chain, with supply chains and logistics is obviously a graph, of course. It's, okay, where should we have this stock of products? So if you know where most of the buying is happening, where most of the things are being shipped through, you want to have that warehouse full of, I'll keep going with shovels, and maybe I'll try to make this into a Minecraft theme if I can, but that's where all the shovels are being bought. We got to make sure that that's going to be stocked full of shovels. And kind of similar to the network outage problem, like we want to know, like if we lose a warehouse, how is that going to disrupt our overall supply chain problem? Pathfinding, which is a classic graph theory, based approach, of course, is wonderful to do in Neo4j generally. It's even more powerful with graph data science because you can do it across, huge amounts of graph data. So again, whether you have a telecom network and you want to find out, the shortest path based on latency, you'd use pathfinding for that. If you want to make sure that there's some redundancy so that you've got alternative paths so that if something does go down, packets can get rerouted some other way. That's all pathfinding kinds of things. Transportation networks, actually each of these examples here, really come down to you've got two things you know about. You want to know all the things in between there and which of those things actually are necessary for getting across. So back to the, if you wanted somebody to talk at a meetup, it's a friend of a friend of a friend. You know both ends. You just want to figure out the path in between. Community detection is a way of doing clustering. So if you have this giant sea of data, you can cluster data based on lots of different things. You can say, okay, I've clustered all my people because they're all people. So that's one giant cluster. Not necessarily helpful, not necessarily indicative of that group of people, like what is actually common among them. An interesting aspect of this is that if you put those people in a graph, and actually I'll jump forward here to this example. If you have all of the customers of, let's say IKEA, if you have all of IKEA customers in a giant graph, it's great to know that they are customers based on region. Okay, so if you have a lot of people in a region that are buying from IKEA, maybe you have to make sure that IKEA store is big enough and stocked well enough for that number of people. But you also want to know, like, what are those people buying? You can actually break down the demographics of people based not on who they are or where they are, but what kind of things they've been buying and actually who they know in their social networks. You can extend all of that into a much richer understanding of customer behavior and then leverage that for things like, sending out coupons or specials on lingonberry sauce for the meatballs that you buy. Okay, I'm going to jump forward here and get to fun. We're going to do a bit of a demo in a little bit. Link prediction is really an extension of the recommendation idea, and it's generalized into the graph data science library, where link prediction takes the idea that what we were just saying for recommendation. So like if I've bought something and you and I are friends, what's the likelihood you're going to buy something else? That is predicting your future buying behavior. So that's one way of taking advantage of link prediction. Link prediction takes a look at everything you know about the a graph in a particular domain and predicts how that graph will grow based on current behaviors. So if all of us are friends and we're not yet friends with somebody who's just walking by outside, but 3 of us are, is that more likely that we're going to become friends with that person because we already have a strong connection within the group. And so that predicts future behavior like friends you might follow. You can turn that into a recommendation or simply anticipate something as well. The other way to think about link prediction is less about predicting the future than filling out something that must be true And the best way to think about this is the classic crime corkboard scenario, where you've got, instead of a beautiful slide here, you have a corkboard with photos and pins and string tying together all these photos that you're looking for who the crime boss is. And you've got all these connections, but you don't know the final connection that draws that's going to let you say, this is the guy. Link prediction lets you realize that there's something missing in your data, that all of the data that you see there, all of the connections that exist, strongly suggest that there should be a connection from this place to that other place. And so it's not a prediction of the future, it's a prediction of something that must exist that you simply don't know yet. So it ends up being, if you would, circumstantial evidence of something that you are missing. And then you can go off and find that thing because the data says it must be there. Okay, and if you can apply that to different contexts, whether it's identity and access management, customers buying products, or customer journeys. Each of these contexts, and I would argue that pretty much every data set you can find is going to have a reason for doing link prediction. Link prediction is one of the foundations of enriching a graph with Neo4j and with graph data science. All right, that whirlwind tour, you may not realize, took us through this evolution of graph data science. It starts with simply having a graph database. It starts with simply having a tool that lets you represent and actually manipulate and query data in the shape of a graph, data that is both individual records and also relationships between those records. Once you've got that, you can start to apply graph analytics, which is just some algorithms that enrich that data. So you start with the data that you already know, you run some algorithms that figure out centrality, that figure out link prediction, figure out whatever else might be interesting aspects or features of the data set, and you enrich that data set with those features. Now the data set is what you already knew from entry forms or from other behaviors, with analysis that now makes it even more impactful. So now the data itself is more useful. That's the graph feature engineering. Once you've got that, you can start to do, so this is all in the unsupervised learning kind of vein, right? Once you've got that, you can start doing supervised learning. Now that you've got an enriched graph database, you can do a graph embedding, basically derive a bunch of vectors. And once you've got some vectors, you can actually apply some machine learning to that and have graph native machine learning. In fact, an entire machine learning pipeline, if you want to, from the raw data to data coming in. You can store the models in Neo4j in addition to the data that the model is about, and have a continuous pipeline that just improves all of your outcomes. Okay, that was a big whirlwind tour. Because now that's enough of me talking. We're going to switch over, if we could, we're going to switch speakers over and do a demo. So we're going to switch machines and speakers. Give us just a minute for that. Thank you.
We had a question? We had a question?
Oh.
Oh. If you could just very short, just
Things just exploded, and then there's this kind of virtuous cycle that ends up happening, where you start with domain data, enrich the domain data, and that in and of itself is already powerful. That's already more useful for building applications and having features that are useful for end users or for kind of classic Tableau style insights. You can do that. That's perfectly great. But it becomes much more powerful when you start to do the supervised machine learning, and then it just becomes more powerful, obviously, with the more data you throw into it.
okay. So
Does that help? Sorry.
yeah, it does. So adding user friendliness to the whole thing and raising the ability to use machine learning on the graph data.
Yes, that definitely is it. And it's something, again, like as I started, like I'm not a data scientist, and yet I can do data sciencey things and like do things that are just absolutely astounding that without these tools would be impossible. And of course, I don't know how the algorithms work, but I just know that the results are doing what I would hope they do.
Thank you.
Testa och plugga in den igen och se.
Jag kunde se den på datorn.
Right, there we are. So I'm gonna do hopefully no slides today. I'm Håkan, I'm a field engineer at Neo4j. So happy to be here. I'm gonna try to kind of go through the things that Andreas covered. So we're gonna start with this very depressing way of looking at data as a CSV file. And we're gonna kind of build a graph out of this and do some fun things with it. So this data set contains diseases and different symptoms. And then there's some weight here that we're going to use. So it's just a long table of data points. So I'm going to use the Neo4j browser, which is kind of a developer tool or a developer interface to learn how to use Neo4j. It's not my go-to tool anymore because like once you get used to Neo4j, you just start writing this in your Python code instead or add it into your notebooks. But for simplicity and to be able to visualize, we're going to use the browser today. So when I want to import my data, I'm going to start with defining a bit of constraints on my database. And this is just a way of telling the database that I'm going to have disease and symptoms as nodes in my database, and I want them to be unique. I don't want to have duplicates of diseases with the same name. So node key here is a way of saying uniqueness where you don't allow null values. Right, so that is a preparation step, and then we're going to load this data right from GitHub. So the command for that is just a syntax to kind of tell the database I want to load something from a file, and you tell it things like how is it separated and so forth. And basically I get every line of data from the CSV file as a row, and I can do things with that row. So I'm going to create a disease node, a symptom node, and then kind of say that if they are on the same line, they are related because that's how the data is organized. So asthma and wheezing, this is kind of a symptom that means you could have asthma, right? So once we have done that, we have our graph. We can kind of go in a random place in the graph and start looking at things. So here we get fever, which has a lot of, is a symptom of a lot of different diseases. So my symptoms are, I'm going to change the color since I'm colorblind. My symptoms are in this blue color, bluish color, and my diseases are orange, right? And we can start exploring the graph. This is usually how I do it when I've imported my first data. I start exploring the graph to get ideas of where I want to go next. Right, so we can see that there is. I was hoping that we can get to something more interesting on the screen here. Let me struggle for a while. Right, so here we can start to see that there's symptoms that are ambiguous. They can be a symptom of many different diseases, as well as diseases have many symptoms. So we have kind of like the traditional many-to-many relationships, right? So if I wanted to kind of pretend that we're going to do some kind of intelligent service that is going to recommend you how to get in contact with healthcare or the right healthcare giver, we could start a query around here and ask questions like, what is a very unreliable symptom? So I could kind of look at what symptom is associated with the most number of diseases, and I can build the result as a table. So your question may be a graph question, but the result may be a table. We can do something more advanced, so we can say what is a likely disease given two different symptoms. So we can kind of walk a longer path in the graph, and that is a general rule. The longer the path you're matching or the pattern you're matching, the more valuable is the answer to the question usually. So if I'm both experiencing fever and swelling, it could be an infection, it could be any of these diseases, right? So my next step here is that I kind of want to try out some algorithm. So if we go back to what the graph looked like, I want to explore this pattern that I have some symptoms that seem to share diseases. We can start running an algorithm to kind of figure out how similar are symptoms to each other. And we're going to run overlap similarity, which has a very simple formula. So it's the intersection of two sets divided by the smallest of the two sets. So what does that mean if I'm going to run that for my symptoms? Well, it means that if I take fever and let's take vomiting here, what is the overlap between these two? So the overlap seems to be only this node, right? And which one has the smaller set of diseases? It's probably vomiting because fever had a lot of diseases. And so when I run this algorithm, it's going to compute the similarity and it's going to build a new relationship in the graph where the relationship will point to whichever had the larger set. So it's going to go from the smaller set to the larger set, right? So that algorithm has a bit of like syntax around it because we need to select our data, give it to the algorithm so it can do its work. And as you saw before, depending on your network, the answer the algorithm gives you will have a different meaning. So that's why I have to go through this work of selecting my data. So I have to put my symptoms in focus here, and I have to collect all the related diseases because those are the sets I want to compare. So let's run that. Oh, that's perfect. My license expired. That happens when you do demos. So let's see if we can sort that out.
December 1st.
So let's see if we can quickly get rid of the enterprise version of things here. Only happens when you demo, right? So let's remove that. And it's saved.
It's just the people in the room, right? There's nobody else. There's no recording of this or anything, right? That wouldn't.
Right, so we're going to give it some time to restart. Just proves that it's live, right? That I'm not making this up or... Right. Good thing it's a database and not all my data was lost. Right, so, and I hope we were in the demo database, I think so. So let's go back to running that similarity overlap. That's better. So, like I said, it will give me a new relationship in the database. Let's see if this will refresh. There we go. So now I built a new network in my graph of how similar different symptoms are to each other. And we can see here that fever is kind of at the top of things and everything is pointing up to fever. And that's because fever was our most general symptom that could indicate pretty much any disease. And by doing similarity overlap, we're starting to almost see that how different things relate to each other, and we're starting to see that, well, chill is a more narrow condition or narrow symptom. So if that could be kind of a question you could ask as a follow-up question to a patient. Do you also experience a chill, or do you? And then you could go in down to like, yeah, do you have a sore throat? No, but I have a snuffle, and maybe it's just a common cold. If you have a sore throat and fever, maybe it's a throat infection, right? Another thing we see here, hopefully, let's see, is that we probably have some relationships we don't want. So we have this where you see this node has a long path or a 2-hop path up to fever, but also a direct hop up to fever. This is one of those things whenever you do data science, and I would say graph data science it's kind of like even more likely you're gonna make mistakes. You're gonna get incorrect results that you want to get rid of. So in my case, I want to get rid of this shorter path and just keep the longer path so it becomes a strict hierarchy with no shortcuts in. Most of all because it's a fun query to show. Because this is kind of the query I leave as a challenge for you to write in SQL or in any other language. So it looks like this. So I want to find a path between two symptoms where there's a longer path, and I want to delete the shorter path, right? So when we have done that, we kind of get a better picture of how things are related. So if you go back and rerun this place here, it will be more a strict hierarchy here around fever, and we've gotten rid of some of these shortcuts. And of course, we can leverage this information now. So if we want to kind of do the same thing we did before, if we're gonna give what could be the disease given fever and swelling, we can also look in the neighborhood in this hierarchy now, and we can decide, do we want to look at more general symptoms, or do we want to kind of go down and only pick more symptoms that are more specific? So we can play around with that now here, and just make the similar thing we had with the product hierarchies before. We can do this kind of variable length walk in the graph to just find what do these things have in common, and well, maybe you don't recall what the numbers were before, but we definitely got anemia up here, so which is a more likely disease given these two symptoms, right? And if we want to have a bit of fun, we can always go back to querying the graph in a way so we just get back what was our original data set. So, I mean, we're still seeing the same data, we're just observing in a different way and hopefully finding new insights by understanding the connectiveness and the connections in the data, right? So that is what I had in store for demo today. And we'll be happy to take some questions from the audience or during the mingle after.
I think we eat first.
Yep.